Okay, so day 2 of chi-square tests, we are going to dig into both the test of independence and test of homogeneity because they're almost identical. And then day 3 is just going to be a practice day. So this is the actual last day of notes. So when you get into the next 2 tests, homogeneity and independence, there's a bit of a summary of those on an earlier slide that we kind of skipped over that's there for you to look at when you are studying later. But basically you start with a two-way table of some type. So you have some sort of groups across the top and groups down the side. And so it looks like you've got 2 variables. It's really how the question is phrased, usually how your last sentence is phrased, that makes the difference as to which of these 2 tests you do. Because other than the wording of the hypothesis and the conclusion and the name of the test, they are identical. So you know the worst thing could happen if you run the wrong one on the AP exam is you give it the wrong name and you lose a point, and everything else is going to be the same. So you typically are going to start with a two-way table, a contingency table. Null hypotheses are pretty much written in stone. The independence is the easiest one to nail down. In the independence test, there's usually a question posed at the end of your problem stem that says something like, is there evidence of an association between the 2 variables? So it's a test for independence, because if 2 variables are independent, there's no association between them. So that's a definition we learned way back many chapters ago. So you will see this word association or the word independence. If you don't see one of those 2 words in your problem stem somewhere, then you're most likely doing the other test. Okay, so the easy part of independence is that the null hypothesis is always there's no association between the 2 variables, and you do those in context. And then the alternative would be there is an association between the 2. There is something going on. For the homogeneity, homogeneous means the same. Okay, to be homogeneous means to be alike. So in a homogeneous test, we're looking to see if some different groups are alike or not. And this is the one that you typically see in experimentation, particularly like drug testing. So if you have like 3 different treatment groups in an experiment, and you want to see if your 3 different treatment groups are the same or different when you're all finished, to see if the new medicine works better than the old medicine, or the new shampoo works better than the old shampoo, or fertilizer A works better than fertilizer B, which works worse than fertilizer C. If you're comparing 3 or more groups and you want to know if they're the same or different, that's a test of homogeneity, a test of sameness. So homogeneity means you have groups that are the same. So it's really about wording. And the independence is the easiest one to nail down because almost always you'll see that word association in your problem stem. So your null hypothesis is that all your groups are the same. The distribution of whatever your variable is the same for all groups, or from group to group. Assumption conditions are the same as for the goodness of fit. So 3 conditions. Data are counts. You had a random sample or random assignment of treatments if you have an experiment. And all of your expected counts are at least 5. So that's good. They're still the same 3. And because these are usually popping up in experiments, we often don't do any kind of generalization of results. And if we're not doing any generalization of results, we don't have to actually check for randomness. But if we know that we have a random sample or a random assignment of treatments, we normally mention it just for safekeeping because that's our habit. Okay, so here's the biggie, all in bold. They look identical except for wording of hypotheses and conclusion and the name of the procedure. So here's your biggie. The best way to distinguish between the 2 is to look for one of those 2 words. If you don't see one of those 2 words, then it's probably a test of homogeneity. Okay, and on the AP exam, when we see these tests, they are very explicit to use usually the word association if they want you to do a test of independence. They will actually, this is how nice they can be, if you call it a test of association instead of a test of independence. I have known them to actually give you credit for that name, even though it's not technically the correct name, but because you understand the idea behind it, I've seen them award full credit for that before. Okay, so let's dig right in. So let's start with the test of homogeneity. So the perfect example of that would be to look at some medicines, an experiment for some medications. So this is sort of the tail end of what we started designing back in Chapter 12. In Chapter 12, we talked about how to design an experiment, and all we ever got to at the end of the experiment was that you compare your treatment groups. But we never got into the details of how you compare your treatment groups. Well, it's because we weren't ready yet. This is the last stage of that procedure. If you run an experiment, after you get your data analysis completed, after your experiment is over and you collect your data, when you analyze that data, you do a test on it. And this would be how you would proceed at that point. All right, so we have these medical researchers. They got 90 subjects for an experiment comparing treatments for depression. So they're probably volunteers who are depressed, which is fine. You don't need a random sample. You just have to randomly assign your treatments. Subjects were divided randomly, we like that, into 3 groups and given pills to take for a period of 3 months. Unknown to them, so blinding is involved, which is the best way to do things. One group received a placebo, so a dummy pill that has no medicinal value. Second group received a natural remedy, St. John's wort. And the third group, the prescription drug, Posrex. Hey, doing all right? Trying to finish up a few last things. I'm down to logging in books and calculators and finishing one last set of notes from Ms. Higgins for the last 2 units that we didn't get to this year because they knocked them off the AP exam.
Stats? Or?
Yeah, it's stats. So I'm making videos for Ms. Higgins so that when I'm gone, she can still teach chi-square test. Okay, thanks. I will too. Okay, so sorry about that. After 6 months, the third group got a prescription drug called Posrex, I guess. So we're trying to probably see if this prescription drug works better than the natural remedy or nothing at all. So it is a well-designed experiment because we have multiple subjects in each group. We have replication, we have randomization of treatment assignment, and then we have control by doing unknown to them, by doing blinding. We can control sources of variation there. Okay, after 6 months, psychologists and physicians who did not know which treatment each person received evaluated the subjects to see if their depression had returned. So because the evaluators didn't know who got what, we have double blinding. So we blinded on the front end the subjects, and we blinded on the other end with the evaluator. So double blind is the best study that you can do. First, somebody has to know who got what, and that somebody is the one who generated the table that we need now. So we'll notice we have a two-way table, and across the top we have the 3 different treatment groups. And then we have what we really want to evaluate. Did their depression return, or is there no depression after those 3 months? So are they depressed? Are they not depressed? Did the medicine work? Okay, so this is sort of a yes-no categorical variable, depression returned or not. So these are the groups that we're trying to decide if they're the same or not. Do these 3 treatment groups have the same rate of depression returning or depression not returning? We want to see if these 3 groups look similar. So are they the same? Now there should have been a question here. Is there evidence that? And that question is missing, which is unfortunate, and we can blame that on me because I didn't get it in there. But this looks like a test of homogeneity. Are these 3 treatment groups the same? Okay, so is there evidence, let's write our own question here, that the prescription drug works better, we're going to use some kind of general terms here, than the other treatments? Because, I mean, let's face it, who wants to know Well, probably the drug company. Because why prescribe a prescription drug if it doesn't work better than the natural remedies or nothing at all? So are the treatments different? We want to run a test. So first thing we do is write hypotheses. And for a test of homogeneity, same groups. Are the 3 treatment groups the same? We would say that they are the same, that these treatment groups are not different. And let's be really specific. The rate of depression is recurrence is the same for all 3. So we'll say in the null that the rate of depression recurrence is the same for all 3 treatment groups. And then the alternative, you squeeze in a not and you've got it. So the rate, and you have to write them out, so don't get lazy on this. The rate of depression recurrence is not the same for all 3 treatment groups. Okay, so to check conditions, we have to have tables with the right kinds of numbers in them. So condition number 1 is that the data are counts. Now the data in the original table, the observed data, are indeed counts. So of all the 90 subjects, 24 in the placebo group had returning depression and 6 did not. In the St. John's wort, 22 had returning depression, 8 did not. Posrix group, 14 had depression return, 16 did not. And Posrix looks quite different than the other 2 groups already, just from a quick glance at the table. But we need some statistically significant evidence before we can really drive our argument home. So these are all counts. These are numbers of subjects. What we don't have yet are the expected counts, and we're going to need the expected counts. So what we normally do, instead of drawing a whole new separate table, is we do a slash in each of the cells of the table, and on the other half of the slash we write in the expected values. Now how do we get the expected values? Well, you do it the long way, which is to tally up the total number with returning depression, and you have to find the proportions of each of the 90 people who should be in each of those categories, and put those back in counts, which is a little bit hairy, and we're just not going to do it. I sort of have reached a point in my career where I don't really teach you how to do it the long way. But if you want to know, you can do the row total, so the total in this row, times the column total, so the total in, say, this column, and then divide by the total, which is 90. So if you want to know what goes in this placebo group, you take the total of this row, and you multiply it by the total of this column, the row and column that group is in, and then divide by the total, which is 90, and it will give you your expected number that goes here. But I like to just let the calculator do it because it's just easier that way. So here we go. We're going to let the calculator do the work. So the first thing is I need some sort of a table mechanism, and it has to be different than just a spreadsheet because I have to have relationships across and down, which a spreadsheet doesn't do. So I actually need a matrix here. So I need to build a matrix. There's a matrix menu in your menus, but you also have a matrix template, which I think is a little less messy to get to. Beside your 9, you have a set of templates, this template button. So if you press that button, you have a whole bunch of templates that pop up. You have a 2x2 matrix in the middle row, third one over. Then you have a 1x2, a 2x1, and then this third one that looks like a 3x3, that's a build your own size, which is actually the one that we need. So we're going to go right there to that matrix template, hit enter, and create a matrix. So we have 2 rows of numbers, so we're going to change that to a 2, and then 3 columns, 3 treatments. And there's our matrix, and all we have to do is put in our observations, and the calculator is going to do the rest. So 24, and the tab is the great magic key that takes you from one cell to the other. 22, 14, 6, 8, 16. Now, I want to be able to reference this when I run the test, which means I need to name it. So before I press enter, or you can still do it after you press enter, it's just extra work, we're going to hit our store key right here. So the store key is above the variable key. We do control store. So basically the store key stores a variable, and the variable key retrieves it later when you need it. And pick something to call it. It does not matter. So I usually just take the easy way out and just do the letter A and call it matrix A. So the first letter of the alphabet, you can call it whatever you want to. You can call it a word, but as long as you can remember how to retrieve it. Okay, so there's our matrix. And now I'm going to actually run the test. So here's the kicker. You have to run the test eventually anyway. When you run the test, it will give you your expected matrix. So if you run the test now, you'll already have all the stuff you need to fill in the blanks for the rest of your procedure. So let's go to menu. Number 6 for statistics. Number 7 for stats tests, and under the goodness of fit test, number 8 is a chi-square two-way test. So the two-way test is for both the test of independence and test of homogeneity, because they both use a two-way table. It's the same procedure for both, so it's all embedded on that one key. So we're going to press 8 to pull that one up, and it'll say, what's your observed matrix? Where's your matrix? Tell me where your matrix is. And I called it A, so all I have to do is type in A, and ta-da, it pulls the data from the matrix and does the test for you all in one fell swoop. So you'll notice you have an extra row here that you didn't have in the goodness of fit test. You have the exp matrix, which is your expected value matrix, your expected count matrix. It's in there. You just have to retrieve it using your variable key. So variable key and the expected matrix. So just arrow down to you have your expected matrix, press enter, and enter again, and there's the expected values. So in a perfect world, if all 3 treatments work the same, the first row should be all 20s and the second row should be all 10s. Do not be disillusioned into thinking that it's always that pretty. It's almost never that pretty. It just worked this way because we had equal sized treatment groups. If we had not had equal sized treatment groups, those numbers would have been much messier. So 20, 20, 20, 10, 10, 10. So we have counts, which is beautiful, and all of those expected counts are at least 5. So now let's go back and check off our other 2 conditions. So the random condition treatments were randomly assigned to subjects. Okay, check. And all expected counts are at least 5. Well, they are. They're all 10s and 20s. So check, check, check. And because those all 3 check, we can use a chi-square test of homogeneity. And it's a homogeneity test because we're checking to see if 3 treatment groups are the same. Homogeneous. Same. You'll notice there's a note over here about the calculator. It'll compute the expected counts if we run the test. And the expected counts in the components matrices can be retrieved with the variable key on your handheld. Okay. So, 2 done, 2 to go. So now let's move on to the mechanics of the test. All right. So because we have 2 different directions, our degrees of freedom are actually a product of rows times columns. So we subtract 1 from our rows, So basically one variable is free to vary in the row direction, and one variable is free to vary in the column direction, so columns minus 1, and then we take the product of those. So sort of like an area, like a pseudo partial area of your matrix. So we had 2 rows minus 1, and we had 3 columns minus 1, so this is 1 times 2, which is 2. It is expected, if you run a chi-square test on the AP exam, that you actually show the computation for the degrees of freedom. So they would expect to actually see how you computed it, so you would want to show this work. It's not hard work, but you have to show where that comes from. And then the chi-square test statistic uses the same formula that we used for the goodness of fit test yesterday. So the numerator, observed minus expected, square it to make it positive, and divide by expected, and do that for each component. Now in this particular case, we have 6 components. We have 6 different categories, 6 different pairs of observed and expected. So we're going to write the first 2, do ellipses, and then show the last one. So for the chi-square test statistic, we'll start with, in the first category under depression return, 24, the observed, minus expected 20, divided by the expected 20, plus, and I usually go across, so let's go to the second row, first row, second column. So observed 22, expected 20, square it, divide by the expected 20. And because I don't want to write 6 of these down, we'll do plus, dot, 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 and then skip to the very last one. So that's the 16 minus 10, quantity squared over 10. And the calculator's already calculated this because I've already run the test. So now I just have to jot down some numbers. So I had a chi-square value of 8.4. That's not nearly as big as the chi-square value we saw yesterday in the goodness of fit test. How big is too big? Depends on the situation. So we really want to depend on this p-value to determine how big is too big. And a p-value is actually 0.014, which is still small enough to reject if we have a fairly normal alpha level of about 0.05. However, often in medical testing, we require a greater standard of proof, I guess, and a lower alpha level is often required. So if you used a 1% alpha level, then this is a fail to reject. It's not enough evidence. If you use a 2% alpha level, this is a rejection. If you use 5% alpha level, this is definitely a rejection. So you have to decide what your alpha level is, and you really should decide that before you run the test, which we didn't do, but we should have. Okay, so the p-value, which is the probability of a chi-square test statistic bigger than 8.4, according to the calculator, is 0.01. That rounds up to a 5. So, depending on the alpha level, that could be a reject or a fail to reject. I just have to make a decision. So, if I use an alpha level of 0.05, then I would do a rejection. So I'm just going to make that decision. So with a p-value of 0.015, I will reject the null hypothesis at an alpha level of 0.05. There is evidence. It's not real strong, so I'm not going to put that word in there. There's evidence that the 3 treatment groups are not equally effective in preventing the recurrence of depression. So what I really want to know, other than the fact that they're different, these 3 treatments are different, which one is the biggest difference and is it a good difference or is it a bad difference? So here's where looking at the component book, the component list is powerful. So I know here that in my original matrix I had St. John's wort in the middle, the prescription drug Posrex on the right end, and the placebo was first. If I look at this component matrix, so go to variables and go to component matrix and paste that in. If I look at the component matrix, I can see that in the third column, which is where the prescription drug was, I see the biggest differences there. As a matter of fact, the really big, the biggie is the 3.6. It's twice as big as any other value in this matrix, and that aligns with the no sign of depression with the Posrex drug. So that is some evidence there that the prescription drug is better at preventing the recurrence of depression than the other two treatments are, because that's your biggest component. So we might, just to strengthen our response, mention something about that. People taking, it's a bad time to run out of ink, because I do not have another pen. Here we go. People taking Posrex appear to be less likely to have a recurrence of depression than people taking St. John's, I'm out of room, wort, or, can I squeeze it, a placebo. Okay, so that gives me a much more powerful conclusion, because at the end of the day, that's what I want to know. Does a prescription drug work better than anything else? And there's evidence that it does. Is it real strong evidence? Not as strong as I would like. So probably to market the drug, I would need to do some additional testing. But I do have enough evidence there that might make it worth the time and trouble and money to do the additional testing. All right, so we're on the home stretch. We've seen the procedure now. So the only difference for the test of independence is that we write our conclusions and hypotheses a little bit differently, and everything in between is going to be the same. So we're going to go ahead and dive in and do one test of independence, and call this chapter done, and then spend a couple days just doing some practice and data collecting and just kind of driving it home. So this is an in-house study. So this is a study in which we're not worried about generalizing it to the larger population, from the New York City Police Department. So it shows the ranks attained by male and female officers in the New York City Police Department. And we want to know if the data provide evidence of an association between gender and rank. So the very first thing I want you to do is underline, circle, do something with that word right there. There's your bottom line. This is a test for independence. Is gender independent of rank? So over here we have the categorical variable gender, and over here we have the categorical variable rank, and we want to know if there's a link between them. If being female makes you more or less likely to achieve a certain rank than if you're male. And this is a very real question that is studied all the time. You know, in the time we live in right now, one of the big areas of study is whether the COVID-19 affects African Americans differently than it affects non-African Americans. So that's been a topic that's been in the news quite a bit, because there doesn't appear at first glance to be independence between is ethnicity the correct word, and whether or not we have complications from COVID-19. So that would be a case where you would look for a study and run a test of independence. So that's quite the real world example that's actually in action right now, trying to get the data to answer that question these days. So you'll notice you have 6 categories. So we're going to have much larger degrees of freedom here. And a lot more stuff to keep up with, a lot more numbers to keep up with. So let's just start with the hypotheses. I'm going to need a new paper. So we've got some blanks here on this next page to write hypotheses. I just don't have my page ready yet. All right, so the null hypothesis. For this one's the easiest one to write. There's not an association. That's what we want to say. So there is no association. Nothing interesting is going on. No association between gender and rank. This hypothesis basically writes itself because it's almost always the last sentence of the problem stem. And then the alternative, you stick a not in there, or you take the no out, sorry. There is an association. There is something going on between gender and rank. All right, so let's check some conditions. Condition 1, data are counts. Oh, and for the record, your calculator will not like data that's not whole numbers. So if you are ever given information in percentage form, and you have to convert it to counts to run your chi-square test, you're going to have to round to the nearest whole number, or your calculator is going to spit it back out because it doesn't like the way it tastes. So you have to have counts, and they have to be whole numbers. Actually, I had a college student text me a couple months ago and was working on some homework for a class, and he was upset because his calculator kept giving him an error message with a chi-square test, and in the end it was because he had decimal values. And like, you can't use decimal values, it doesn't like it, you'll have to just round. The second one is randomness. Now here's the thing, this is not a random sample, but we're not generalizing to the bigger population. We just care about what's going on in the New York City Police Department. It's like an inside investigation. So the results are going to only be applied to this group. They're not going to be applied to a bigger population, which means we don't actually have to check for randomness. So randomness, not necessary, results will not be generalized. So this is just really a note to you. You don't even have to write that down on the AP exam. You can just skip right past that one. We do have to check to see if expected counts are at least 5, which means we're going to have to run the test on the calculator to get our numbers. So we're going to lay this aside, go back to the table, and get our expected values. So let's make a matrix. And I'm going to actually start a whole new document so that I don't have yesterday or the last problem's gobbledygook mixed in with my new data. So I'm going to build a matrix. So I'm going to go to the template key beside the 9. The last thing I used there was the build your own matrix. It's still the first thing available. I have 1, 2, 3, 4, 5, 6 rows and 2 columns that need to receive data, and let's just input some data here. The good news is you would not get anything this cumbersome on the AP exam because they know you have limited time. And all they're looking for there is, do you understand how to run the procedure, why you should run this procedure, how to interpret what you get after you run the procedure. That's the important stuff. So they can give you much smaller groups, much smaller numbers for that study. All right, remember to arrow to the right of the matrix and to name the matrix. That's just easiest. So control store and call it whatever you want to. I'm a creature of habit. I call it A every single time. So it's stored, and now we're ready to run a test. So menu, statistics, stat tests, chi-squared two-way test, same as we used for homogeneity. Tell it the observed matrix. You have a drop-down menu that you can choose A out of, or you can just type in the letter A. Doesn't really matter. And the test is run. And notice you have a really, really, really large chi-square value. Look at that, 290. That's enormous. And look at your p-value, times 10 to the negative 60. You have 59 zeros after the decimal before you get your first non-zero digit. Highly, 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 highly unusual, virtually impossible to get a sample this interesting, which means something is going on. We just have to write it all out and explain what it is. So let's get our expected matrix right here. So variables, expected matrix. We can pull that up so we can get some numbers, and those are horrendous. So what we're going to do is just truncate. You can round or truncate. It does not matter. All that really matters is that those are bigger than 5, and they are. So what I would want to do is do /22249/4133/3665. I really am just truncating off the decimal values, because all that matters is the calculator knows the truth. What's on paper is just a general idea of the sizes of each group, the size that each group should be. So we're going to definitely just truncate. If you want to round instead of truncating, entirely up to you. It doesn't matter, because what really matters is these numbers right here. That's what we're going to have to deal with. But before we dig into those mechanics, let's go ahead and finish up our conditions. These are definitely all at least 5. So we can check that last condition. All expected counts are at least 5. Check. Do a chi-squared test of independence. Alright, worst is over. All that's left now is some mechanics and a conclusion. And we already have all the numbers we need for that. We just have to copy them down. So, mechanics. Degrees of freedom. Our number of rows, that was 6 minus 1, times number of columns, that was 2 minus 1. 5 times 1 is 5 degrees of freedom. And you'll notice on your calculator that's confirmed. Degrees of freedom is 5. Chi-square test statistic is observed minus expected. So I've got to go to my table. These are huge numbers. 21900 minus expected 22249 squared over 22249 plus ... I really should do 2. And then the last one, 10 minus 34 squared over 34. So show how to set it up. The chi-square test statistic, according to the calculator, is 290.13, which is huge. The p-value, which is the probability of a chi-square value bigger than 290.13, is 1.32 times 10 to the negative 60th power. Virtually zero, virtually impossible that you would see these numbers if ranks and gender don't have an association, if there's not something going on. They are not independent. So here comes evidence for some sort of corrective action, lawsuit. There's definitely going to be a shakeup somewhere, because this is highly unlikely if there's not something going on. Okay, so conclusion. With a p-value of nearly 0, I will reject the null hypothesis at any reasonable alpha level, so just pick one. There is overwhelming evidence of an association between gender and rank. Something is wrong with this picture, in other words. So where's the biggest discrepancy? So that's where the component list comes in handy. So it's time to take a look at the component list. We have yet to actually work one out together where we failed to reject. If you failed to reject, there's nothing interesting going on. There's no need to even look at the component list. But because something interesting is going on, we should look at components. Let's take a look. All right, where are the big numbers? Here. Oh, there's a really, really, really big number. There. These two middle ones. So if I look at the corresponding places in the table, so in the female officers, sergeants and lieutenants, if we look at the differences, the observed number of females in those ranks is less than what's expected by a substantial amount. So we're seeing in those ranks a discrepancy. In really, if you look at the male side, discrepancies aren't very big. None of those are really huge. But for females, you have, for the officers, you have more than you should in the officers. You have less than you should in these higher ranks. So you'll notice as we go up the ranks, your expected numbers are larger than your observed numbers, and in the lower ranks your expected numbers are lower than your observed. So the higher ranks are less likely to be awarded to females. There's a disproportionate number of females in the higher ranks, disproportionately low, and disproportionately higher number in the lower ranks. So that's going to lead to some sort of action, probably. In particular, let's comment on what we just saw. Women are overrepresented in the lower ranks and underrepresented in the higher ranks. Not so much for men. Sorry if that was off the page. Men, pretty typical distribution. Somebody's going to have a problem with that. And somebody's going to raise a stink. And there's going to be some news about that, probably. All right, so let's wrap up this last bit. The homework for today is page 698, 131, and 33. So some practice to do on your own for those two-way tests. And then we're going to add just one more item to the day 3. Since we've got the page out, we might as well go ahead and write it down. Number 35, and I'm not sure the page number, but it's just a continuation, plus some FRQs in class just for funsies. And we'll see that when we get there. Maybe collect a little more data, just manually collect some data and do some sort of evaluation of that. All right, so chi-square test all wrapped up. Calculator does most of the work. As far as number crunching, pretty much does all the work. And it really just is about learning this new structure for the procedure. All right, we'll call it done.